questions?
Yes.
Yes?
A friend of mine will come in about.
He will be coming, okay.
Two minutes.
I will give the explanation to him as well.
Could I also have a pad for the...
Pad? What do you mean? Oh, this?
Yes.
Yeah, I'll get, yeah. I have another one. This is your family?
Yes. Yes.
Okay, welcome. So that is your seat. You from 3 o'clock to follow the meeting. And then, well, then you stay here for a while. There are all kinds of amenities. You might have seen it from others.
Yes.
A speech and then when you are back in your seat, I leave. Yeah. Okay, your feet. Then you. This is your. You are supposed to sit next to him. If no one. For me, it's fine. But this is the official way. That is fine for me. So, and afterwards we will bring you there. Don't stay here too long. After the reception, I will ask you to go there quickly because we want to congratulate you. Oh, you can do that afterwards. Yeah. No, the books we can do that later. Yeah. Okay. Success. Enjoy.
Thank you very much.
Yeah. I'm walking around. If you have questions in the meantime.
Okay, thank you.
Okay. Success.
Finally here, huh?
Yeah.
I remember the very first day of bachelor's, you were saying you wanted to do a PhD, and I was like, whoa, you really think a long time.
I don't know. I love it. Good things. I had a very good update meeting, so now I'm all set.
Hopefully this goes well too.
Ladies and gentlemen, thank you for coming to my PhD defense. My name is Emmanuel Sunil, and before I begin today, I'll give you a brief overview of the plan for today. So first, I'll give you a short presentation of about 20 minutes about my topic, and then after that, there will be a short break of about 10 minutes. Then exactly at 3 o'clock, the defense will start and will last for exactly 1 hour. After the defense, the committee will sort of go to their committee room to decide whether or not I should graduate. And hopefully, if everything goes well, around 4:30, the graduation will occur around here. Then after the graduation, at around 4:30, there will also be a reception, which is the Franz von Hasselt Saal, which is just behind here. So you just have to go outside, turn to the left, and then walk to the back, and you will see the reception room. So as the title slide says, my PhD topic was about analyzing and modeling the capacity of decentralized air traffic control. But what is decentralized air traffic control? Well, before I talk about that, I want to give you a little history lesson about air traffic control. So in the very early days of aviation, aircraft were very simple machines. They consisted of just wood and linen, and they had very simple instruments on board, usually just a compass. And because the traffic demand at that time was very low and only very few people knew how to fly airplanes, there was very little aircraft in the air. And in fact, for that reason, there was no air traffic control. But of course, as technology progressed, air travel became more popular, and especially in the 1920s, aircraft became advanced enough for carrying passengers. Here you see the famous Fokker 3 motor, or Fokker 7 as it's sometimes called, and it was one of the first wooden passenger aircrafts in the United States. Now, because traffic demand started to grow, there became a need for controlling the traffic on the ground, especially, so that there were no collisions at the airport. And because of that, the field of air traffic control came into being. And it had very humble beginnings. So this is widely recognized as the first air traffic controller. His name is Archie William League, and he was an air traffic controller in St. Louis Airport. And he used very simple tools, such as colored flags, to motion aircraft and to tell them when to start and when to stop, these kind of things. But of course, as traffic demand kept on increasing in the 1930s, it also became important to control the traffic not just at the airports, but also in the air in between the airports. And we had the creation of the first en route air traffic control centers. And at these centers, the air traffic controllers would use flight plan data and keep track of all the flights in the air to determine potential collisions between aircraft. But they had no direct contact with the pilots, so they were calculating the possible collisions purely based on the flight plan data. After World War II, radar technology was introduced into air traffic control, and for the first time, air traffic controllers could see a live image of the traffic that they were controlling, and with two-way radio, they could also talk to the pilots on board and give them instructions on how to avoid collisions. And in this way, air traffic control has evolved over the years with increasing levels of automation. However, one thing hasn't changed, and this is the most important part. The air traffic controller remains at the center of the picture. The entire system is designed with the air traffic controller, the human air traffic controller, in mind. And one of the results of this system is that we use these things called airways, especially at high altitudes, to navigate. So for instance, this is the airway map over the Netherlands, and these lines indicate the airways that aircraft are allowed to fly over. So these are like highways in the sky. And the reason for using this is because airways make the traffic picture on the radar screen pretty simple, and that makes it possible for the air traffic controller to see the conflicts and regulate the traffic. However, as you can probably tell, there's a lot of empty space in this figure. So not all the airspace is being used. And also, these routes, they were defined a long time ago based on the location of navigation beacons. And these routes haven't been updated based on the changes in the traffic demand. So we're stuck with this sort of airway system that dates back to the 1950s, in fact. Now, as you can imagine, as traffic has been growing over the years, this system is nearing its saturation levels. And you can often hear people talking about delay statistics and how delay is becoming more and more every year. And that's sort of an indication that this current centralized system is nearing its capacity. Now, to solve this problem, researchers have been looking at decentralized air traffic control. Well, the best way to explain it is to compare it with the current centralized system. So today, we have an air traffic control on the ground, and he communicates with all the traffic to separate them. In decentralized air traffic control, the pilots, using inter-aircraft communication links, are able to detect the conflicts themselves and solve these conflicts without aid from the ground. So it's sort of like autonomous cars, but for planes. Now, the reason we want to do this is because we can change the routing structure. So we can transition from the current airway routing in en route airspace, so that's the area of airspace where aircraft are cruising, to more arbitrary routing. Each aircraft can fly its own route, whatever route it likes to fly. And that is expected to increase capacity because that will spread out the traffic more evenly over the airspace and use the available airspace more efficiently. So previous research has suggested that decentralization will increase the capacity of the airspace. And there's been a lot of research in this area. Is the video working? Not really. Okay. So the video here was showing the airborne separation assurance system, which is sort of the system that is on board the aircraft in the decentralized scenario to help aircraft detect conflicts and resolve them. There's also been other research in the areas of cockpit displays and flight simulator trials. And a lot of this research has been done here in the Netherlands at the National Aerospace Laboratory of the Netherlands. But even though decentralization is not a new idea, in fact, the idea dates back to the 1960s and was initially proposed by air traffic controllers themselves, it has not been implemented anywhere in the world. And this is probably because of many technical open challenges that remain for decentralization. And in this thesis, I really focused on 3 of those technical problems. The first problem has to do with airspace design. How should you structure the traffic to maximize the capacity for decentralization? The second aspect has to do with safety modeling. So you have different ways of structuring the traffic. How does each structure affect the safety of the airspace? And the third aspect has to do with capacity. So different ways of organizing the traffic will obviously have an effect on the capacity. So is there a way that we can create mathematical models to be able to predict that? So this is what my thesis is about. It's about answering these 3 open problems. And my overall research objective was to analyze and model the effect of airspace structure and airborne CDNR on the safety and capacity of decentralized air traffic control. And I specifically focused only on the en route phase of flight. So let's take a look at the first one, which is airspace design. And this project was done as part of something called the Metropolis project, which ran between 2014 and 15, and it was a collaboration between TU Delft, NLR, ENAC, and DLR. And in this project, we used fast-time simulation experiments to compare different airspace structures, and then we tried to use the results of those simulations to determine how capacity varies with the level of structure in the airspace. So we looked at 4 different airspace concepts, starting with the completely unstructured full mix concept. Then we added one constraint, which is the layers concept, where we had heading altitude rules, so each layer limited the range of travel directions that is allowed. Then we had the zones concept, which again added another constraint, so we had 2 constraints this time, where the horizontal routes of aircraft were predetermined. And finally, we have full structuring, which is called the tubes concept. And in that concept, both the X and Y position, as well as the speed, or you can look at it as time, and the altitude of aircraft are all pre-calculated before takeoff, and they're supposed to stick to this pre-planned route as much as possible. So we used fast-time simulation experiments to compare these 4 concepts in terms of capacity. And what we found out was that the best concept in terms of capacity was the layers concept. And this was really surprising to us because most of the literature on this topic focused on the completely unstructured full mix concept or the tubes concept. They hadn't considered any kind of transition airspace structures. And the reason why the layers concept was really good was that it allows horizontal direct routing in the horizontal direction, but in the vertical direction, it limits the range of relative velocities. So that means that conflicts are less likely to occur in each layer. And this was found for not just nominal situations, but also for non-nominal situations. So this is also a very robust concept. So the second part of the thesis was about safety modeling. And in the safety modeling part, what we wanted to do is, in a sense, generalize the results of the first study. So the first study gave us some indications on how to structure the traffic to improve capacity, but it didn't tell us how the design parameters affect the number of conflicts in the airspace. So to understand that, we used conflict count models. And conflict count models are very simple. They've been around and they've been used since the 1960s. In fact, they were used to design the North Atlantic organized track system. And they consist of essentially 2 factors: the number of combinations of 2 aircraft multiplied by the conflict probability, or the average conflict probability, I should say, between any 2 aircraft. And using this very simple construction, you can calculate the number of instantaneous conflicts in the airspace. And here's some math, but the main novelty that we had in this thesis was that we were able to compute the 3-dimensional conflict probability, whereas most of the previous results had focused primarily on the cruising part and did not consider the fact that aircraft also have climbing and descending phases of flight, which is also relevant for en route airspace because you have to climb to your target cruising altitude. So in this way, through these equations, we were able to calculate in 3D the conflict probability between aircraft. And we did this study for just 2 of the concepts that we started out with, because these 2 were found to be the most promising from the 4 that we originally considered: the unstructured airspace concept and the layers concept. And here's a sample of the simulation results that we did. So what you see here in the cloud are the simulation data, and the lines are the model predictions. And we did this for 5 different airspace concepts. So you have the unstructured airspace, and then 4 different layered airspaces. And the difference there is the heading range that's allowed in each layer. So for instance, in layers 360, all heading ranges are allowed in one particular layer, whereas in layers 45, the heading band is only 45. So you need to have multiple layers to get to all your possible travel directions. And what we see in this figure, first of all, is that the model is really able to predict the number of instantaneous conflicts in the airspace quite accurately, because the solid line really goes through the middle of all the simulation data. And the second thing that we notice is that reducing the heading range per layer for reducing the heading range per altitude for layered airspace concepts really increases the safety of the airspace because the number of conflicts decreases. And you can see here from the different spacing between the lines that this increase in safety is quite nonlinear. And when we looked at the results, we were really able to predict this phenomenon quite accurately. And what's also important in this graph, in the second graph, where I show the conflicts categorized according to category, is that the proportion of climbing and descending conflicts, which is showed here in blue, really increases as the heading range per flight level is decreased. So climbing and descending aircraft become more relevant when you decrease the heading range per flight level. And this wouldn't have been possible, you wouldn't have been able to predict this without having a 3D conflict model. So with the 2D models that were there before, you would never be able to determine what the effect of climbing and descending aircraft are. And for instance, for the layers 45 concept, 78% of the conflicts were caused by just 12% of the aircraft, because only 12% were climbing and descending. So it's really important to take into account all phases of flight when you're modeling conflicts. Another thing was that these models, they make a lot of assumptions regarding the behavior of traffic. In fact, they make basically 4 different assumptions. But we also found ways to generalize the models to take into account each of these assumptions. For instance, if you look at the spatial distribution, the model assumes a uniform spatial distribution of traffic, like this figure. So, but then we managed to come up with adjustments to the model so that it can take into account hotspots in the traffic. So for instance, in these 2 figures, in these 2 traffic samples, there were deliberate hotspots created in the center. And when you look at the simulation results for the 3 different cases, so here you have the uniform case, and then here you have the 2 hotspot cases, you see that the adjusted model is able to take into account the different spatial distributions of traffic. And this makes the models even more generalizable and even more applicable to today's situations, for example. And the final part of the thesis was about capacity modeling. Now, the first thing I want to say is that safety is not the same as capacity. And you may have already guessed by the fact that I had these 3 open problems, and safety was not the same as capacity. But it's really easy to see that safety is not equal to capacity when you look at the North Atlantic organized track system. So this is a airspace design that is used by traffic traveling between North America and Europe and vice versa. And essentially, it consists of some predefined tracks over the airspace. Now, you can quite easily see that if you increase the separation between these tracks, you will make the chance of conflicts much less. But if you do that, the number of tracks that you can fit into the same airspace would be less. And so you can increase capacity, you can increase safety, but at the same time decrease capacity. So safety and capacity are not the same thing. So if safety is not equal to capacity, perhaps one way to look at safety is to look at different metrics at the same time. For instance, safety and efficiency. The problem with this is that what weighting do you give to safety and what weighting do you give to efficiency? Well, what would be better to have is a metric in between that takes into account safety and efficiency at the same time, and then you can use a single metric to directly measure capacity. And literature suggests that that metric is stability. And stability considers the occurrence and propagation of conflict chain reactions. Well, what is a conflict chain reaction? Well, very simply, we can take a look at this system with 3 aircraft. And we have a conflict here defined between A and B. Well, if A turns to the right to solve this conflict, it can trigger a new conflict with C. So it's created a new conflict as a result of the first conflict. And that's a chain reaction. And then C could also turn to the right, and that could also create a new conflict with B. So now we have 2 extra conflicts because of the first one. And this phenomenon can be computed using something called the domino effect parameter. And that's why on the back of the thesis, there's a picture of the dominoes on the back cover. And the domino effect parameter can be computed using a very simple equation. And the output of this equation is essentially the number of secondary or follow-on conflicts triggered per primary conflict, so the initial conflict, which is a measure of the number of chain reactions in the airspace. And so the nice thing about the stability way of looking at capacity is that conflict chain reactions implicitly take into account both the efficiency and safety of travel without any weighting. Because conflicts reduce the safety of the airspace, and chain reactions also increase the flight distances that aircraft have to fly, because each conflict will have to be resolved, and so that will increase the flight path of aircraft, either distance or time. So they decrease the efficiency of travel. So in this way, you can take into account both safety and efficiency at the same time without having any weighting factors. And if you have a higher domino effect parameter, then you have a lower stability of the airspace and therefore a lower capacity of the airspace. Now, using this idea, we came up with a definition of the capacity of the airspace. And what we essentially said is it's quite a theoretical definition. What we said is that if you take the limit of the derivative of the rate of change of the domino effect parameter with density and set the limit to infinity, the density that causes this limit to go to infinity, that is set to be the capacity of the airspace. So at the capacity of the airspace, as per this definition, all aircraft are stuck in a conflict chain reaction. And they continuously perform conflict resolution maneuvers and are not able to fly to their destination as a result. So they just get stuck in this sort of endless loop. And that density where that occurs is what we define to be the capacity of the airspace. Now, of course, this is a very theoretical definition of capacity, and it's mainly used for comparing different types of airspace designs with each other in a very unbiased way, so you don't have to use these weights anymore. So this way, you can have a sort of a very fair comparison between concepts. Of course, this is not the same as the operational capacity of the airspace, which has to do with things like economics, airline economics, and other factors. Now, we have a framework, a 6-step framework, that uses the domino effect parameter and some of the results from the previous safety modeling exercise to compute the capacity of the airspace. And again, we did this for unstructured and layered airspaces because they were the most promising from the first study. And if you take a look at some of the simulation results, what you see here in the points are the simulation data. Here's the domino effect parameter. Here's the density. And you can use the domino effect parameter equations and the framework equations to calculate the maximum capacity of the airspace. Essentially, what you have to do is find the density that corresponds to the vertical asymptote of these curves. And what you see here is quite interesting. So again, we have the same 5 concepts, and you clearly see that the layered concepts have a higher capacity than the unstructured one, but the layered ones don't seem to have the capacity is not really different to each other, whereas before we saw that the safety was much better as you decrease the heading range. Now you can take a look at the underlying equations of this framework and explain this. Essentially what happens for the safety is that the conflict probability part actually decreases. So it becomes more safe as you decrease the heading range. But at the same time, you also decrease the efficiency with which you solve the conflicts. So on the one hand, you increase safety, but that increase is canceled out by the decrease in efficiency with which you solve the conflicts. And so there is no change in the capacity as a result. And again, this means that safety is not the same as capacity. So this leads me to my conclusions. And very briefly, I have 4 main conclusions. The first one is that capacity for decentralization is maximized when you use this layered airspace concept with heading rules, heading altitude rules that separate the traffic vertically in the airspace. The intrinsic safety of an airspace design is affected by these 2 factors, the number of combinations of 2 aircraft and the average conflict probability between any 2 aircraft. And airspace designs that reduce both these factors improve safety on a strategic timescale. Then we came up with this framework, which we called CAMDA, Capacity Assessment Method for Decentralized Air Traffic Control. And that framework defines capacity using conflict chain reactions. And it defines the maximum capacity as the density at which conflict chain reactions become completely uncontrollable, and they propagate throughout the entire airspace. And the last conclusion is that The capacity of a decentralized airspace system is dependent on both the airspace design and the CDNR algorithm. For instance, with a layered system, we saw that you could increase safety, but the CDNR algorithm was solving the conflicts inefficiently as you reduce the heading range per flight level. So you need to optimize both airspace design and CDNR algorithm and the pairing between these two things to maximize the capacity of the airspace. And that's the end of my presentation. Thank you. So there will be now a sort of a 7-minute break, and after that, the defense will continue.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Emmanuel Sunil, Master of Science in Aerospace Engineering. De verdediging zal in het Engels worden gevoerd. I request the candidate to go to the lectern. First of all, a warm welcome to all of you who are here to witness the public defense by the promovendus of the dissertation entitled Analyzing and Modeling Capacity for Decentralized Air Traffic Control. The Board for Doctorates of the TU Delft has installed a committee to evaluate the thesis and the propositions. This committee will now have a public debate with the candidate. Before we start, it's an honor to present the members of the committee to whom I extend a hearty welcome. Starting at the opposite side of the table, going counterclockwise, the first opponent is Dr. Brian Hilburn from the Center for Human Performance Research in the US. Next to him, we have Professor Danielle Delahaye from École Nationale de l'Aviation Civile in France. Then we have Professor Hartmut Fricke from TU Dresden in Germany. Then next to him, Professor Dirk Küchler from DLR and TU Braunschweig, also in Germany. And then we come to this side of the table, where all parties are actually from the Faculty of Aerospace Engineering. We have Professor Dick Simons to the most left, the co-promoter, Dr. Joost Ellerbroek, to my left and to the right, the promoter, Professor Jacco Hoekstra, like I said, all from the Faculty of Aerospace Engineering here at Delft University of Technology. Thank you all for taking part in this committee. My name is Henry Werry, and I'm the Dean of the Faculty of Aerospace Engineering, and it's my pleasure to chair this session on behalf of the Rector Magnificus. I now would like to start the opposition and give the word to Dr. Hilburn, please.
Thank you, meneer de Rechter. Waarde promovendus, first I'd like to extend my congratulations on this work, on the breadth of work, the depth of the analysis, and the quality of the writing and the production. You're to be commended, so congratulations on that. I'd like to start out with just a quick question of clarification, if I may, regarding the layered concept and the distinction between UA, the full mix, and what you call the L360. I understand that the only difference is the presence of flight levels in the L360 condition. And excuse my ignorance, I'm a bit puzzled by the fact that there would be such a dramatic, roughly 30% difference in conflicts between the L360 and the fully mixed. I could see actually there being more conflicts in an L360. So my question is, could you clarify just a bit? Is it, for instance, that aircraft are berthed pre-separated in the L360? What is it about the two that would explain the reduction?
Zeer geleerde opponent, thank you very much for your kind words about the thesis and also for your question. So your question relates to the difference between the unstructured airspace UA and the layers 360 concept. In the layers 360 concept, indeed, there are predefined flight levels. And these flight levels do two things. First of all, they decrease the number of combinations of two aircraft. And second of all, they change the conflict probability equations between unstructured airspace and layers 360. In unstructured airspace, conflict probability is a function of the volume of airspace search for conflicts, whereas in layers 360 for cruising aircraft, it's a function of the area search for conflicts. Mm-hmm. And the area is smaller than the volume, and therefore the conflict probability is less for layers 360. So in fact, it reduces the number of combinations of two aircraft and the conflict probability between any two aircraft in layers 360. And as a result, it increases safety.
Thank you. You suggest that, early on, you suggest that there's as you put it, a pairing between the selected airspace design and the chosen CDNR algorithm that needs to be optimized. That pair needs to be optimized to maximize its capacity. Perhaps I missed that thread running through the results, and it was addressed somewhere, and I missed it. One example is the tube concept, I know, that has the vertical and horizontal constraints, meaning that speed is the only parameter available for conflict resolution. What did you mean by that, and are there other examples? I realize that the modified voltage potential theory was the one CR algorithm used, and I was curious whether you're referring to the experimental level, vertical, horizontal, off of the MVP, or whether you were speaking more generally there about the MVP versus other potential algorithms. Could you just discuss generally what possible interactions there are that you were referring to, interactions between airspace concepts and algorithms?
Yes, indeed, your question refers to indeed the relationship between airspace design and conflict detection resolution. I made this comment in the conclusions based on the results in Chapter 5. And this has to do with the comparison between unstructured airspace and layers concepts in terms of capacity, and capacity there is defined in terms of conflict chain reactions. Now, in Chapter 5, I used the MVP algorithm, modified voltage potential algorithm, And the results showed that there's no significant difference in the capacity of the layered airspaces. So you had different layered airspaces compared, and the layered airspaces differed in terms of the heading range per altitude layer. And in chapter 3, when I decreased the heading range, there was an increase in the safety, whereas in chapter 5, when I decreased the heading range in terms of conflict chain reactions, there was no increase in capacity. Mm-hmm. So this increase in safety did not translate into an increase in capacity. And the reason for that is, although the layers is making the airspace safer, they do result in, as you decrease the heading range, they do increase the proportion of conflict chain reactions that occur in the airspace. And that has to do with the fact that the MVP algorithm does not take into account the airspace design when it's resolving conflicts. It simply tries to solve the conflict first, and then after the conflict is solved, the aircraft has to return back to the airspace constraints. And when this happens, and because the conflict is being resolved without consideration of the airspace concept, what happens is that the pairing between airspace design and airspace conflict detection resolution is not very good, because in layered airspaces, as you decrease the heading range, what you end up with is conflicts that are further and further away. So the closest point of approach becomes further and further away. And the way the MVP algorithm works is that it tries to ensure the separation at the closest point of approach. And as a result, there is a long distance that the aircraft have to fly before they can fly back to their pre-conflict destination. And so essentially what is happening is that as you decrease the heading range, the efficiency with which these conflicts are being resolved with MVP is decreasing. The extra distance that you have to fly to solve one conflict is increasing, even though the conflict probability is decreasing. And so these two factors are canceling each other out, and that's why the layers didn't increase the capacity of the airspace. And that's why I say that to increase the capacity of the layers further, you should come up with an algorithm that is more in tune with the fact that in layered airspaces you get these faraway conflicts.
Thank you for that.
Are you satisfied with the answers, or would you like to ask another one, a short one perhaps?
If I may ask
Yes, please
one more?
go ahead.
Thank you for that. One final question, and it concerns sort of at a high level. This was an exploration of the theoretical limits of airspace concepts with respect to capacity and safety. Could you have, as I understand it, the CR algorithm can resolve heading speed and vertical issues. Could you have flipped this around and looked at it as a conflict resolution problem? Perhaps I'm sort of confusing the tactical and strategic timeframes here, but I'm wondering whether you could modify a conflict algorithm with, say, layer constraints and approach the problem not as an airspace one at all. You've got, because at the end of the day, the fully mixed airspace concept has 0 constrained degrees of freedom. Can you set aside the whole airspace problem and say this will be a conflict resolution algorithm problem, adding some constraints? Because it seems to me that without addressing what the airspace looks like at all, you could achieve everything with the CR algorithm, or not?
Okay. If I understand correctly, you're asking what is the purpose of airspace design, and can airspace design be effectively compensated for by just using a very good CR algorithm?
Can we assume it's the Wild West airspace everywhere?
Yes.
And the onboard algorithm will do everything, including containing the constraints to achieve
Yes.
layered performance?
So indeed, you also mentioned in your question strategic and tactical timeframes. And in the ideal case, I would say that you should use both. You should use strategic. You should try to prevent as many conflicts as that could occur in the strategic timescale, and in the tactical timescale, you should try to solve whatever is left. So if you have a good airspace design that tries to prevent a lot of conflicts from occurring in the first place, that decreases the amount of work that the tactical algorithm has to deal with during flight operations. So it is good to have both at the same time. Now, of course, you could you should try to tailor the algorithm, the conflict resolution algorithm, to the airspace design that you're using. So for instance, in a layered airspace design, instead of using the MVP algorithm, I would suggest that you use an algorithm that tries to solve the conflict as quickly as possible, rather than use an algorithm that tries to use the minimum deviation resolution maneuver, which is what MVP tries to do. So I think you need to have both to achieve the safety in the airspace and the capacity in the airspace.
Thank you.
Are you satisfied with the answers?
I am, thank you.
Thank you very much for the opposition. Then I would now like to give the word to Professor De La Haye, please.
Thank you, Chairman. So, wat promovendus? Sorry, I'm not so good for that, but first I have to say I really appreciate your report. It is really clear, really easy to read. So it is a nice piece of work, a good work and a lot of work, I think. So definitely it's a good report. I've also appreciated, as a mathematician, as a nice derivation of some closed form or formula for the conflict resolution, conflict expectation. But I have some questions for you. The first thing, because I'm coming from the operational system, and why such a decentralized approach is not used today for the real aircraft? According to you, just a general question. What is the main limit?
Hoogleerde opponent, thank you very much for your kind words on the thesis and also for your question. So your question relates to why decentralization is not being used today.
Right.
I think this has a combination of two aspects. The first is technical, and I will talk about that first. And then the second is, I think, social and political issues. The technical reason, I would say, is that decentralization is yet to be implemented anywhere in practice. And therefore, there's no hard evidence that this would really work when implemented with all kinds of uncertainties, wind, all kinds of things that happen in the real world. And so we need to have that data first to gain the confidence that this could really work in practice. And that is not yet available. So we have a sort of and to be able to do flight tests, you need to have some confidence that they will work. So you have a little bit of a chicken and egg problem. There's not enough, let's say, willpower. This is the political aspect, to invest more in decentralization, because it's not completely certain that this will really work. And that has to do with the political aspect. And the social aspect is to do with the fact that decentralization implies more automation. And automation in this regard does lead to reduced use of human labor. And of course, that's always a little bit controversial. Right now, air traffic controllers are involved in the system, human air traffic controllers. If you were to go to a decentralized system, of course, you won't replace all of them, but you will replace a considerable amount. And people are not very much fond of replacing high-paid, high-skilled human jobs. And I think this is the social element. So I think a combination of these three elements, and I think the technical ones are also still valid, and the social ones are also equally valid, have prevented decentralization from being implemented in practice.
Thank you. Okay.
Please go ahead.
So for your model in the fifth part, I was a little bit surprised why your limit capacity appear when you have the first failure. When you have the chain reaction coming. But according to me, I think that the limit capacity appear when you have the first failure of the conflict resolution algorithms. When you have the first failure, I think it is the beginning of the capacity. But you go at the extreme. Why you choose such extreme?
So indeed, we chose the case where there are infinite number of conflict chain reactions in the airspace, as opposed to as soon as there's one loss of separation, for instance. I think this has to do with the question. The reason we went for the extreme case is because we felt that, well, one loss of separation, a loss of separation doesn't automatically mean a collision. It just means separation standards have been lost. And it could just be a one-off event. So if we were to define capacity as soon as a loss of separation occurs, well, practically you would have a very low airspace capacity. Even today, we have loss of separations all the time. Even in today's traffic mode of operations, the centralized system, we have loss of separations every now and then, not all the time, every now and then. And if we were to say that today's demand is already too high, and then we would have a problem. We are in fact exceeding the capacity of the airspace already when we have one loss of separation. I think in a feasible way that doesn't seem to be the right way to go. We decided to go for the other extreme, where all aircraft are essentially in a conflict situation, because this is easier to compare different airspace concepts. If you were to say 1 or 2 or 3 or 4 or 5, then you would have to come up with a valid reason why 1 or 2 or 3 or 4 or 5, and it seems always very arbitrary. Whereas if you were to say infinite, then you are really looking at the system from a high-level dynamics point of view. You're trying to understand the underlying dynamics in the system, and you can then derive the equations that relate parameters such as look-ahead time with the capacity. Whereas if you were to limit it to 1 or 2 or 3 or 4 or 5, that relationship wouldn't be so clear, I think. That's the reason why we went for the infinite.
That makes sense, just to compare between concepts.
Indeed, in a fair way.
With number, okay. Yeah?
Yes, you have time for another question. I have one question. Could you perhaps speak a little bit closer to the microphone? Because
Sorry.
For the audience.
Sorry,
Thank you.
forgot. As another one, but do you think, because you have extracted some closed forms for the expected value of the conflict number?
Mm-hmm.
And my question is, do you think that some closed form formula could also be derived for the standard deviation?
Yes, I do think it would be possible. If you know the full distribution of the various parameters, such as heading difference, velocity, you should be able to calculate the standard deviation as well. The reason we didn't do that is because we are interested in airspace design, and we're interested in, and because of in the airspace design world, we're interested in truly occurring conflicts, not the conflicts that are being perceived by the aircraft themselves. So the real conflicts from the system perspective, and therefore we are really interested in the number, the actual number, and not the standard deviation.
Uh-huh. And perhaps the last one?
Yes, please.
Okay.
For short.
And just a more general question, according to you, among the 4 concepts, which one could be preferred by the controller?
I think among the 4 concepts that I compared in Chapter 2, full mix, layer, zones, and tubes, I would say that the controller would prefer the zones concept the most, because that is closest to today's mode of operations, where you have predefined tracks in lat long, and that's essentially what the zones concept is.
Thank you very much.
Are you satisfied with the opposition?
Yes.
Okay, thank you very much. Then I'd like to give the word to Professor Fricke.
Warte Promovendus, also congratulations from my side, specifically for improving the final version over the draft version. This has become now a very clear piece of work, so congrats for that. I would like to open the questions with a similar aspect. You started your work obviously being convinced when I'm going to release boundaries, when I'm going to go for decentralized traffic, I find the maximum of capacity usable for air transport operations. However, when you look into recent activities like continuous descent operations into busy airport, free flight airspace issues over Hungary, so there are some pieces of work already operational being tested and trying to improve operations by releasing boundaries. But after all, everyone found immediately that capacity drops since, let's say, the variations increase. So can you give me once again your initial motivation, how you started the work and why you believe that this is a good way to go ahead?
Hooggeleerde opponent, thank you for your kind words on the thesis. I enjoyed revising the thesis also. And also thank you for the question. So your question has to do with how whenever constraints seem to be free to traffic, the capacity seems to reduce in today's operations. I think today, as you mentioned, we have some FRAs in certain parts of Europe where free routing is allowed. But in these cases, the controller is still responsible for separation. The aircraft are not given that task. I believe that for a decentralized system, for these constraints, when they're given back to the aircraft, they have to be given fully to the aircraft. The decision-making power has to be given fully to the aircraft. And I believe that is the reason why it is not, the capacity is not improving as expected, because well, when constraints are given back in a centralized system, this makes it more difficult for the air traffic controller to monitor the situation, because now he has to keep into account all kinds of different things and not just aircraft on one line, for instance. And that's more difficult for the human brain. I don't blame air traffic controllers. I would find it very difficult myself. And that is why when you give up constraints back to the aircraft, with a human air traffic controller still in charge, the capacity doesn't increase as we expect because of the limitations of the human workload factor. Yeah.
Just a little add-on, when you consider it from the optimization perspective and you interpret in saying the precondition is to handing over responsibility entirely to the aircraft, to the flight deck. This looks to me like searching for local optimi. So for the optimum per aircraft, because every pilot crew is intended to use best airspace on their own, compared to a, let's say, ATC-centric perspective, where the system would rather look for a general or global optimum. So again, we could fight for saying, that's obvious what's going on depending on whether or not you delegate tasks to the flight deck. Maybe you can just give a little extra on that.
Indeed. So you talk about the difference between the local optimums that could occur as a result of decentralization versus a global optimum that could be theoretically realized with a centralized system on the ground. I completely agree that you would be able to realize a global optimum if you had a centralized system on the ground. However, there are all these uncertainties that have to be taken into account. And these uncertainties are changing in time. And I think that is the reason why it's better to aim for a local optimum, which is still better than the current situation, than a global optimum, which is, let's say, probably could be better, but it's hard to realize. I think because of all the uncertainties, winds, differences in human performance, reaction times, all these things will have to be taken into account to achieve a sort of a global optimum. I believe that's too difficult. I think because of all these interactions between all these different elements, achieving this global optima will be much harder than achieving the local optima, which is still better than today's situation using decentralization.
Okay, this brings me to my next and probably last question. So about the metrics you're using to judge the different results of your simulations or trials. It is a lot about capacity, as the title introduces. And you're also linking capacity implicitly to safety, complexity, efficiency. This is what has been stated in your conclusion. So I think that's quite a risky statement. But let me to start on, you're just introducing the CAMDA logic.
Yes.
Using CAMDA to figure out where this uncontrolled chain reaction is going to start. And you're using the parameter DEP-DAP in order to calculate its volume. So on page 155, you gave that equation where the theoretical areas of conflicts, depending on whether or not you introduce in conflict resolution, are being shown. It's represented by RA, R1, R2, and R3. And what I'm missing in that equation is the temporal aspect. So I would expect to see something like a minimum look-ahead time required to consider conflict resolution as being true, correct. So that's like a precondition in order to hop from one conflict resolution procedure to the next one.
Yes.
So to solve the entire problem of a given term in time. So can you just elaborate why I do not find this parameter in the formula? Maybe just a final statement, even though you're introducing that parameter, LIT, look ahead time, in your definition point in chapter 1 or 2.
Thank you for this very interesting question about essentially, I think the question has to do with why am I looking at the stationary sort of situation? Traffic is always evolving in time, and shouldn't that be taken into account when you look at chain reactions? Is that correct?
That's correct.
So indeed, the Camden capacity definition looks at this extreme case where all aircraft are stuck in conflict. So in this case, what is essentially happening is that the chain reaction has propagated throughout all parts of the airspace, and such that all the aircraft are essentially one continuous conflict chain reaction. And because of this situation, there isn't really a change in number of conflicts or change in potential solution directions or things like that at this extreme traffic density, at this capacity point. And for that reason, we can look at the system sort of as a sort of a stationary situation, unless something happens to the system. For instance, you remove some aircraft, they decide to leave the free flight airspace, and then there's some extra volume available for solving conflicts. It is a sort of a stationary situation at this extreme capacity point. And that's why I don't have time in that particular equation that you're referring to.
And you do not think that this changes, at least depending on what I'm saying, the time sequence between one conflict and the consecutive next one, so the head conflict being produced by the conflict resolution, this portion of time should vary depending on the density.
Indeed, I think at lower traffic densities, I think you're completely correct that the time element will have an effect on the progression of conflicts. If you were to look at a simulation and you were to stop it immediately after one conflict occurs, well then, of course, you don't have any more conflict chain reactions. But if you were to allow the simulation to progress, indeed, you may see more chain reactions occurring or these chain reactions dissipating in the airspace so that they're stopped. So indeed, I think this happens at the lower traffic densities, whereas at the higher traffic densities, the situation doesn't change much with time.
Okay. Thank you.
Thank you.
If you want to, there is time for another question. So.
Oh, that's great. Thank you so much. So I have one more. We just started on debating that, let's say, by email, honestly. So it was about the flight level allocation scheme concept you were introducing, or level band allocation concept, where you said for each 45 degrees in heading change, I'm allocating the next 300-foot level. So it takes me 8 times 300 foot in order to find the next vertical layer, allowing me to fly in the same direction, right?
Yes.
So as we know, reduced vertical separation was a tremendous effort and success in order to increase capacity en route. So one would obviously assume that this definition is very sensitive to the result. So my question is, if it's not, I would suppose that there is no vertical variability considered in your model. So you're saying altitude height keeping is considered to be 100% at all times? This is my guess. Yeah. And if so, argue why you did that very formal precondition for your experiment.
I think I would like to answer this question using a figure in the book. Okay, so here you see a sort of schematic of the layered airspace concept with the 45-degree heading range that you mentioned. And indeed, you would need 8 layers to have all possible flight directions. So if you have, as you suggested in chapter 2, we had a vertical separation requirement of 150 feet, and therefore I used a layer height of 300 feet. Because one of the requirements for the layered concept is that the vertical separation has to be at least equal. The separation between the layers has to be at least equal to the vertical separation requirement, so that aircraft in different layers, when they're just flying, they don't automatically result in a loss of separation or a conflict. So you can always decide to increase the height difference between the layers. So for instance, in this chapter, in chapter 5, the vertical separation requirement is 1,000 feet. And in this chapter, I've used a layer height, zeta, of 1,100 feet. So as long as the height keeping error does not vary more than 100 feet, then the equations would still result in the same results. So a little bit of height, as long as you design your layered airspace with some margin in between the layers, you would be okay with the height keeping errors.
So explicitly stated, it means you do not consider vertical variations of the flight track, since you say the buffering is big enough in order to compensate for any potential slight variations.
That's correct.
That is your statement.
That's correct, yes.
Okay, thank you.
Are you satisfied with the answers?
Yes, I am. Thank you.
Then I thank you for your opposition, and we go to Professor Kukler to continue the opposition.
Well, thank you very much, and also congratulations for this important work, especially when we look at the situation in air traffic control in Europe last summer, and we are facing next summer, I'm pretty sure, on capacity constraints. So my first question is related in general, it's a rather general question. You mentioned several times that for ADS, or for the use of self-separation, you use ADS-B, Automatic Dependent Surveillance Broadcast, also as the it's on page 17, the key enabling technology for airborne collision detection or conflict detection and resolution. I'd like to elaborate